Right, hi everyone. So yeah, my name's Andy Stretton and I work for a company called Zagami. And under the hood of our product, then we've been using quite a lot of asynchronous Python to make things work faster, but also to reduce the number of dependencies so that it can be just installed on any user's laptop. So yeah, for this tutorial, there's a few things that you can be setting up. So the first one is MongoDB. If you want to play around with MongoDB, just install it from the website. And also, on top of your basic Anaconda install, then there's the distributed package and also Luigi package. And then AIO, HTTP, timeout decorator, and motor. So all of this stuff's on the Slack channel if you want to take a look there. So yeah, what is Zagami? What are we going to cover? So we're going to look at how can you use all the processes on your machine when you're running a simple data science script. And we're going to demonstrate this by doing an image processing algorithm over a art gallery data set. So in this case, I'll just show you quickly what it looks like, what the final output looks like. So this is our tool Zagami, and here we have a scatter plot of the x and y parameters. And these x and y parameters have come out of a TSNE algorithm. And so the idea of that is to cluster the images and find out sort of similar images. Then you can use this. We allow people to then use our tool to help them tag and annotate images, but it could equally be used for generating machine learning data sets, self-tagging. I mean, it hasn't worked that great, but there's some interesting separation going on here. Okay, so back to the tools. The next thing we're going to take a look at is how do you consume social media data as it's being produced. So if you go to stream on Wikimedia, you can actually see all the changes that are being made by people to Wikipedia. So you can see the scroll bar here on the left-hand side, right-hand side, just increasing as data comes in. So handling this kind of a data set, either producing it or consuming it, is a great application of asynchronous frameworks. And then, obviously, when we're asynchronous, we've got to not waste any time sort of blocking and waiting for things. So we need to then be able to write this data straight into a database, but not necessarily wait for confirmation. Let the exceptions be handled somewhere else. Then we're going to take a look at how do you create a simple task scheduler loop. So typically, if you had to make something happen once every second, you might create a while true or something simple like that. But asynchronous frameworks give you a lot of power to do things like this. Also, then, this is an interesting one because all of these async frameworks, whether it be Tornado, async.io, or concurrent futures is kind of async, all of them sort of purport to give you a timeout against the function that you're calling. But as we'll discover, things are not that simple in Python. You can't necessarily time out a function and throw an exception if it takes too long. It may just carry on running in the background anyway. Then we'll look a little bit at what the architecture of Jupyter Notebooks is. and then think about how can we use WebSockets in the most simple way. Because when I was trying to learn WebSockets with Tornado, I always saw these really big examples with all the different routes built. And hopefully in this talk, I'll show you a super, super simple one that everyone can understand what's going on. So, yeah, I guess to start off with some definitions of what we're talking about. So, concurrency means that more than one thing is happening at once, basically. And that's not actually, it's not synonymous with asynchronous. Asynchronous is the antonym of synchronous, but concurrency is neither asynchronous nor synchronous. It could be one or the other. Oh, wait. No, that's fine. And then also we have this concept of futures. So I like to think of a future as like an IOU from whatever system for a piece of data that you've asked it to produce by running a function. So these things are called promises in JavaScript. So if you ever learn JavaScript, you'll end up using promises. And futures are very similar, really. You can wait for them, and you can do things when they're finished. Then you've got this concept of an executor. So these are a set of threads or processes that you just create, put there, and then send some tasks to them. So rather than, say, creating a process or running a script for a task, you're actually creating a holder process that then you can throw some things into it. So it's a bit like a road. It's there after all the cars have gone, effectively. And it has then a number of lanes as well, so you can say how many processes, how many threads. That determines how much capacity it's got. And then, yeah, as I say, it doesn't move around anywhere. Even when the cars have all driven through, then you can close it down, or it maybe just stays there depending on the framework. So in the standard library, we've got two executors, the thread pool and the process pool. And then in this little example here, then we open up a thread pool, and we can submit to the thread pool, and then future.done will return as false straight away. But if I actually go to my notebook, then I run this function. Yeah, it's returned as false. I wait a little bit. I run the next one, and it returns as true. So you can see in the background that's being run, and the future is holding the state of that particular function call. So, yeah, just to sort of reiterate, we haven't had to do anything in our own business logic to check whether it's complete or not. So, then we also have executor.map for processing lists of data. So this allows us to send a whole lot of data off to be processed and get back some futures for it. So this is the next example. We're processing some prime numbers, or finding out whether these numbers are prime or not. Now, where are we? Oops. Yeah, so then all of the numbers come back and done. So we're having to call, what are we calling here? For number prime into, yeah, I can't. So yeah, sorry, the function itself is printing out whether, I'm not sure what should print. Yeah, anyway, we carry on. Then for the other thing that's really useful is to use the as completed iterator. So what this allows us to do is to chuck a whole load of data to be processed and then get it back in the order that it comes back to us. So here, I have no idea which order these particular functions will return in. So we have 0, 2, 3, 4, 1 this time, but it will be different every time. So I guess for the first exercise, that if you want to get involved in that, it would be to perform this TS&E analysis on this art gallery data set. So it's kind of slightly contrived, but what we're doing here, we're downloading a CSV file, then we're downloading the images, we're replacing the images and converting them to linear arrays of pixels, so the same operation as was done in the previous talk. And then we're performing this TS&E analysis. So if So yeah, if you've downloaded has anyone who wants to kind of got hold of the notebook if they want it? I don't know. But in the notebook folder, we've got this ashmolean.py file. And here we're we're getting the data just with standard library requests. So this is completely basic stuff, really. Pulling back the data with requests and aggregating it together. So once we've aggregated the data from the requests library, then we can process the images one by one. Now, the question is, how do we make this work with multiple processes? So, and moving on to sort of the answer, then we only actually had to change the run section of the implementation. So all of those functions that we had didn't need to change at all, and we could just parallelize it by first creating a process pool executor, submitting all the tasks to be processed, and then going through them as completed and calling this result function. So result on a future gives back the result of it. But that is slightly different whether it's a tornado future or a future coming from concurrent.futures. Then finally we sort of submit them back into the pool to be processed again, wait for the completion of the data, and then run the TS&E algorithm. There's no parallel version of TS&E available in scikit-learn, so yeah, there's not much we can do about that. There is a C-based version that we could try if we wanted to get really fast. So to conclude this sort of part of it, then we're able to run the processing across multiple machines. We don't really need to change the code. And we could, if we want to, open lots and lots of threads to pull back the images off the internet. So what is async, and why would we do it with async? Well, async is really a change in the flow control of the program. So this can be somewhat tricky to understand. So I've got a little sort of analogy. What is asynchronous Python? So let's say I'm trying to make some toast and make some fry some eggs at the same time. Then I've got all these different tasks that I need to do in parallel with one another, so that at the end of it, I've got hot toast and hot eggs on top of it. So there's a few ways we could do this. So procedural way, let's say I've got a really crappy old toaster like this, then I can try and toast the bread, but I've got to watch the toaster while it's doing its job. So how am I going to get everyone's toast cooked as well as their eggs? So I'd have to maybe half cook the toast, turn it off, and then go cook the eggs and turn. So, and this is somewhat analogous to what you would do, what we're doing in the original version if we're not using parallel processes. Then when it comes to multi-process, then you've got two people cooking the breakfast together, and you can communicate with each other. And yes, if you do it right, it all works fine. But it relies on you being able to run two different processes on your machine. I mean, multi-threaded, maybe that's me with both my hands cooking both the toast and the eggs. Yeah, I can do it. My brain has got to consciously switch between looking at the toast and looking at the eggs. So this context switching is the whole point behind asynchronous programming, as in normally if I open 500 threads on my computer, then the computer itself is deciding when to context switch between those threads, when to leave one of them running and jump to the other one. And actually, as we'll see, they're really, really good at that. So some of the reasons that people maybe give for, oh, isn't async programming great, are a little bit bogus in some respects. So in an asynchronous methodology, then I'm throwing away my old toaster and I'm getting one of these toasters that can detect whether my toast is cooked or not. And this was actually developed back in 2005, way before the Internet of Things. So don't let any Kickstarter startups tell you otherwise. And then maybe I want to cook my eggs carefully, so I get myself a Heston Blumenthal 1-degree precision poacher. So I've put together the best things I can have to cook my breakfast. Now I can simply set off my toast, set off my eggs. Maybe I have time to set off my vacuum cleaner too, go read the paper and eat my breakfast. So that's sort of the idea behind asynchronous programming. We're setting all these things off, but it's me that's doing it. I'm not having to use two hands. I've got all my concentration on one task at a time, but I'm setting these things to run in the background and then coming back to them when, say, they beep. So the toaster beeps, the egg poacher beeps, and I can just go back on the event and get on with the job. So what is that idea of cooking breakfast, how do I express that programmatically? So we send a task off to be run that requires no processing at all on my machine. We get back an acknowledgement. So say with MongoDB, we're getting back just MongoDB saying, yes, I've received something, but we're not getting back what MongoDB's done with that piece of data. And then we wait using this future object. We do some other stuff in the meantime. Finally, we hear an event and go back to what needs finishing off. So concurrent.futures also allows me to wait on events. And I guess Asyncio and Tornado take this one step further because it's all happening in one thread rather than happening across multiple threads. And the reason I sort of mention async.io and Tornado is because essentially a lot of the other frameworks that are out there in Python for this sort of stuff have fallen by the wayside a bit. Asyncio is now in the standard library, so you'll obviously need to know that. Tornado has probably got the best documentation and the most examples out there out of all these libraries, so you probably end up using that one too. So here's a little example of async.io. So what we're going to do here is sleep for 8 hours in 10 seconds. What I sort of mean by that is with 3,600 parallel tasks, sleep for 8 seconds in each of those tasks. So, here we Is that running? Okay, runtime error. Sorry about that. Event loop is clear. Oh, maybe I've. Yeah, I think these. Sometimes in the Jupyter notebook, it's a little bit difficult to run this kind of task, but so typically I just switch to the terminal. So Python, if I had it here. So I've got the Tornado version here. So we're sleeping for 8 seconds and then we come back. But the point is that in order to actually get back out of the loop, then, or to hand flow control back to the I/O loop, then I'm using this yield from command. So there's a few things that you sort of have to get right to create one of these async.io tasks. We have to use yield from. We have to use an event loop. We have to wrap the function call in a task. And then we have to wait for it in the right way. And when we're actually inside the function, we mustn't do anything that's blocking. So then in Python 3.5 or 3.4, then there's a new keyword, async. So what you're going to start to see around when you see a project these days is you'll start to see these async and await keywords. And really the two things are effectively the same. So async.io.coroutine is exactly equivalent to async def bar await. So yeah, I guess this is the most modern way to go about it. So yeah, we always have to have this coroutine. It's wrapped in a task. The sleep function is also a coroutine, so anything that you call inside the function is a coroutine too. Then you've got this yield from and await. So it's sort of similar in Tornado. So again, we've got this special sleep command. And we're using yield instead of yield from in this case, which is slightly confusing, I find, but there we are. And then here at the bottom, loop.runSync just means run one function in this loop. Because one of the things I found really weird about using Tornado was that you start setting up an I/O loop instance, and let's say I sleep with that I/O loop there, then it's still open and it's still running. But if I don't tell it to stop, then I don't know how necessarily to stop it. So we have features like run sync and run until completed, which allow you to just run a standard sort of Python script in one of these async frameworks. So then, now it turns out that we can still do the same thing with thread pool executor and concurrent.futures. And what's actually happening here is that we're sending all these 3,600 things into the thread pool, and the CPU itself is deciding, oh yeah, I've seen a sleep, or the way Python is implemented on the CPU is deciding, oh, I've seen this sleep. I can just move on to a different thread, because we've only got 8 processors. The computer can only be doing 8 things at a time in a way. Then it's switching between them intelligently. And actually, when you run these two examples, whether the Tornado or the thread pool executor one, the thread pool executor is actually faster, which surprised me slightly, but perhaps it makes sense. Now, the other thing to note is that in Tornado, it actually does work under Python 2, but the only way we can break out of a coroutine in Python 2 is to raise an exception. So there's various new features in Python 3 which gives us more options. So yeah, there's loads more different kinds of tutorials, simple tutorials from Yirei Diaz here. So if you want to read up more about, or we may get time to look at more of them later. So yeah, we keep seeing this event loop thing and this I/O loop. So what the hell is it? So it's got all these different names: message loop, message dispatcher, message pump, run loop. It's something that waits for and dispatches events. So I guess one way to think about it is to think of a loop that is producing one kind of event. And then we can move on to sort of understanding what that is at the system level. So if we're streaming Wikipedia, then we can actually read that URL synchronously. So here we've got a nice simple request.get function. We can iterate the lines of the response, and we get back data, print it out. So if I go back to my example, yeah, so it keeps printing more and more output, and it's getting back all of that. So I'll stop that. So the question is this way of pulling back data from Wikipedia, is that really compatible with Tornado's I/O loop? Can I just use something like this and then push it into Tornado's I/O loop so that I can, say, write it to MongoDB without waiting for it to say yes? And the answer is kind of no, right? This iterator is blocking. So for some part of the time that it's iterating over that HTTP request, it's stopping the whole execution of that particular thread, which then in turn will stop our I/O loop from turning round. And therefore, if we try to use it with Tornado, we're going to have some situations where tasks can't be run. So that means we need a non-blocking read with Tornado. So this is, to get a non-blocking read in Tornado is not too bad. It's not too difficult. We've got this async HTTP client. We can run a client.fetch method, and then we specify a callback to be called every time that we receive some data. So, and we'll get very similar output to previously, except that what's actually happening here is that we're receiving raw packets. So that's raw bytes of data coming back from HTTP. Therefore, we've first got to encode them in UTF-8. We've then got to build them up into our JSON objects, which is kind of pretty low level and annoying, to be honest. Now, if you're just reading straight from a socket server, then Tornado has a method for reading line by line, but it doesn't when it's HTTP. So that means, yeah, we have to add all this extra bump to look where a particular piece of data started and build it up into a JSON object, check whether it's a real JSON object or not, and then if there's some sort of leftover, we have to keep that in the thread and wait for the next piece of data to come. So that's what the self.partial data part is doing. So that's great, it works. But then, how do we save those to the database? So we save them to the database by, in our streaming callback, because in this particular case, we are in the context of a Tornado coroutine, and that means that we can call other Tornado coroutines just like their standard functions. So in this case, we're calling db.testcollection.insert1. So yeah, you can pull down this example and test it out. No. The trouble is, though, this is still a lot more complex than the requests example. I don't really like all this complex back and forth code. There's also 2 different callbacks. So we were hoping to write cleaner code using futures rather than using callbacks. So also you get this weird thing going on with Tornado is that, or with async Python, and something to watch out for is that if I have an error in my data, I can't remember what the error was in this, but let's try. Right, so I've just okay, so now my entire IPython notebook has had to restart and everything's crashed. And this is quite interesting because that means I've thrown an exception during the system's I/O loop. And what's even more kind of annoying, really, is the stack trace, because what does any of this mean? It's kind of, how am I supposed to interpret this? Okay, so I'll go back. I think I'll have to run that as a single file. I think. Let's test. So yeah, even what would typically happen is that okay, so there's been a HTTP error, and when we look back through the stack trace, then we know it's come from simple. Okay, so we're trying to decode the input as ASCII, and what's interesting, what was really confusing for me when I was first learning about Tornado was that, hang on, I've thrown an exception here in data equals input.decode ASCII, but then I don't get any other information about the actual function that I was really running and the full stack of how that exception got thrown. So if we think a little bit about what's going on there, the reason for that is that the global I/O loop is the thing that's running my code, and it's become detached from the original place where it got called. So the way that this then sort of gets handled is an interesting one, and that's where some of the other frameworks like Dask distributed handle it a lot better, because what they can do is natively package the exception inside of the future, so that when you call your future later, when you call the result method of your future, then you get the exception back. So then, how does AIO HTTP handle this? Well, yeah, we have to install with pip. It hasn't got a conda package yet. It's quite new. The docs aren't that great, but we do get all the new language features, and suddenly we're able to do these asynchronous iterators over the response. And it all looks very similar to what we did previously using requests. which is quite neat, really. So I guess one of the tasks for the end is, can you now marry those two things up? So Tornado implements a async I/O bridge. So and there's these two I/O loop classes that you can use instead of the standard I/O loop, and that will give you access to both a Tornado I/O loop and an async I/O loop. Then you can use Tornado where it makes sense, i.e. WebSockets or whatever is better documented for Tornado, or you might have a framework that's already using Tornado, but you can sort of attach an async I/O loop to it. So that will be interesting. So what have we learnt about async HTTP? Well, we've learnt that Tornado and async I/O work really well for external HTTP requests and things where something else is doing the work. We always need this future to wrap around it. And where there's some sort of blocking call, then the process pool executor can be used sort of alongside of Tornado. So you can sometimes have a Tornado web application with a process pool executor inside it. Now, ultimately, though, some of those things aren't that recommended, and maybe that is why when we get to looking at how IPython Jupyter notebooks are architected, you'll see there's usually some kind of middleman between the async code on one side and the synchronous code on the other, because that makes the whole thing probably easier to test, and you can be sort of sure of yourself a bit better. So the next one is to look at this terminal clock. So here I'm just printing out the time over and over again, and I can sleep for an amount of time that adds up to a second and keep printing the time over and again. So the question is, for later, how do you implement that using Tornado and or using an I/O loop? How do you keep printing out the time to the console? So the next thing I was going to cover was, how do you run a task in Python and time out if it takes too long? So yeah, as I said earlier, it seems a really obvious, simple thing to do, but actually there's further difficulties in that both the process pool executor and, say, async I/O or Tornado, they have cancel functions against their futures, but all that does is it throws a cancelled error against the loop and sends the context back to the loop so the loop can carry on running. But your process could still be dancing away merrily, deleting all the files on your computer or whatever it's doing. So, which I found really unhelpful and strange, but it's all to do with perhaps how Python is implemented in C. So here, for example, I can run until complete. Oh, what was? Sorry. Okay. Sorry, my notebook is not correct there. Bad. until complete. And execute loop. Sorry, I have to move on from that one. The next example is where we are timing out a task with signals, and this mostly can work on Unix, but not necessarily on Windows. It would depend on the situation. So in this case, this timeout decorator package allows you to just wrap your function call in a decorator and then time out if, and that, at least in this case, the process has been killed. But you then ask the question, well, is this definitely a scalable solution that will always work? Is it right to be kind of killing processes at the OS level like that? It's not great again. Another one is to kill the process using so subprocess. The subprocess module has this ability to kill off a process after a timeout. So yeah, that's great. So we've shelled out effectively, and then it can work. But then with all these methodologies, we've got possibilities of zombie processes, lack of control, and then we've got frameworks that say they support task cancellation but don't. So I guess the best way that I have found to do a timeout and to specify it when I'm running the task is using Luigi. So Luigi is a task runner developed by Spotify, and we can run this particular task here. Oh no, sorry, I've forgotten how to run it. So we see that one task failed because it timed out. So if we then reduce the sleep time or increase the timeout to 11 seconds, and the task was successful. So great, we've done a little bit of a tour of asynchronous Python methods. Now we get back to our image processing task. The thing is that we've seen with Jupyter and with random crashes like this, often we don't necessarily want Tornado to be running the whole app for us, especially when there's lots of things that can go wrong. So the question is, how can we... Okay, I'm being timed out. Yeah, I'll get my power pack in a moment. How can we run this this? Oh, where am I? How can we take advantage of this async HTTP, but at the same time not have all of the difficulties of Tornado being the main, of the I/O loop being the main sort of process that is running our tasks? So I guess what I'll do, I'll just go get my power pack and I'll leave anyone who wants to download any of the stuff, the URL up here. So So Dask distributed is a framework that's built on Tornado and also Fred Pool executor. And it works similarly to the Fred Pool executor, but what it allows you to do is it allows you to scale from your laptop up to a cluster. And you've also got access to this running I/O loop where you don't really, as long as you don't do anything silly like raising an exception in the I/O loop, you don't have to worry about sort of starting the I/O loop, putting it in a separate thread, and so on. What that means is that you can actually use workflows like what I showed for requests and Wikipedia without having to worry too much about doing stuff async, but you can still have async as a way of communicating your tasks between the different workers. So there's also these data structures. So if you're interested in doing big data processing with tools like Dask, which is quite interesting in the sense that it gives you the full range of features of Python over a big data set, over a distributed system. Whereas if, say, I'm using PySpark, then perhaps I can't run. I have to change my algorithm almost to make it fit with the PySpark way of doing things. So it's quite an interesting tool. You can also pass around queues. So you can take a multiprocessing queue and you can pass it straight across a cluster of machines. So the workflow is pretty similar. Now, we can either use the I/O loop instance on the worker client to pull down the images, or we can just carry on using multiprocessing or multi-threading on a particular worker. So I've got the two examples here. So we run when we're running the task on the cluster, we just do client.submit run on cluster, then it goes away and runs it. And then if we've got a sort of driver loop for our application, we can use something called the worker client, which will go through all of the tasks and run them from one of the workers as a client to all of the other workers. And you see that the syntax is relatively similar to what was done previously using process pool executor. So we're just importing everything from the previous file because, again, the functions don't need to change. Then, in the case of Tornado, then what I found was that it was often possible to get slightly more data over the network using Tornado because just because of the way web servers work, really, if you're sending 10 requests at once to begin with, you're probably overloading the web server a bit. But Tornado, by definition, is never sending all of the requests exactly at once. So the data starts to flow back to you in a bit more of a stream. But more or less, they're pretty similar. Although, again, there was more messing about to be done with the Tornado way of doing things. So here I have to keep a thread pool count for myself and so on because it's not implemented as standard in Tornado's async HTTP client. So then, sort of getting towards the end now, and we're looking at how do Jupyter notebooks work. So as the talk said earlier, then we've got a number of different systems going on. We've got the browser, the notebook server, where there's this WebSocket communication. We've got the kernel, where we've got 0MQ communication, which is, again, they're all, both WebSockets and 0MQ, you can think of them as working very similarly to the Wikipedia example, except in their two-way communication as well. So the point is that the single-threaded nature of Tornado makes it ideal for keeping all these different browser tabs up to date. But then again, if you have one little bit of latency in any of the system, then you can very quickly get overrun. So one little bit of disk blocking in the functions that you're calling. So the next example is Tornado Vidi Printer. So on port 8889. So we see start, and then after a short while, we see finish. And so that's one HTTP request that I'm writing to slowly in my own time. And that's very similar to the way WebSockets work, but I just wanted to create a very simple example to show you that this this is really relatively easy to do in Tornado, whereas in any other Python web framework like Flask, etc., that runs off UWSGI, you obviously can't do this kind of streaming request. Oops. Oh, can we go back to the tutorial page? So the final sort of thing is this uber simple WebSockets repository. So I wanted to show you this because this was the first time I'd really seen a really simple WebSocket example in Tornado to sort of get you going, to get you understanding it. So what they've done here is say, right, we're not gonna render the HTML even. We're just going to show you how does the simplest possible WebSocket handler work, and how does that connect up to JavaScript. So what's happening here is that the WebSocket is sending the values with this function here. We've got an open function, so effectively we're opening an I/O loop when someone comes and connects. We're opening a periodic callback per user who comes and connects to our web server. Then we're sending back some data every 2 seconds. So and then we can just browse to wherever you've pulled that repository to using the file : / URL, because we've just got a simple HTML file. So, and every 2 seconds, our graph gets updated. So this is just hopefully the simplest way for anyone who's never really used a WebSocket before to understand how these things work and how to make a really simple real-time dashboard. Then we also have a little notification. So I'll just go. I guess I'll go through the summary, and then if you want, we'll sort of finish there, and you can play around with some of the examples, hopefully. So we've learned how to use process pool executor and thread pool executor to run tasks, and they can watch the status of these futures. We've learned how to make these HTTP requests asynchronously. We've learned how to follow this streaming API from Wikipedia, how to time out the running of a function, and then we've looked at how you can combine this async HTTP with processing on multiple machines. But I think probably the main reason you'll end up using asynchronous frameworks is for messaging, etc. So those are probably the best sort of applications for this. So I guess I'd like to thank Zagami for letting me do this. Matthew Rocklin, so he really, this I suppose is a real nice story in a sense that I came to Dask Distributed never having used Tornado before, and I was actually starting to contribute some things to the documentation and making lots of mistakes. And Matthew really encouraged me, and that was so cool. And I would say to anyone who's never made an open source contribution, if you at some point got frustrated with a piece of documentation, try to correct it. Yeah, you'll probably get it wrong, and they might correct you. But everyone will have, that won't be a problem, you know? Send your pull request, you'll get to know some people, and you'll actually learn more about the frameworks that you're using. So, yeah, and obviously, if anyone's interested in like using Zagami for generating machine learning data sets or other applications where you've got loads of images and data, come and talk to me. If you want to work for us in Oxford, come and talk to me. And yeah, just one last little demonstration. So yeah, Python in the browser. Okay, cheers. So yeah, any questions? Any particular ones that you want to drill into a bit more? Good. I guess in that case, we'll. Yeah. Right.
Just an observation. Isn't it true that the core routines are a much smaller footprint than tasks or processes? That's one of the things.
Yes.
Substantially so that you can scale like order of magnitude above tasks.
Absolutely. So as we're moving, and I think this becomes, I've obviously done my tests on a really powerful laptop, and as we're moving towards a situation where typically you're running on maybe half a CPU on a Docker container, then actually getting the most out of your network and the most out of your CPU like that and running on one, what can you do the most in one thread becomes relevant. Yeah, I suppose, I think it all depends on exactly what you're doing. When it comes to latency and so forth, then WebSockets will always win, right? So, and any kind of socket-based communication will always win. But what I suppose I was trying to get across was that there's so many things that you might try to do with Tornado just because, but actually concentrating on those things maybe is more relevant. I'm not sure. Hard to say. Okay. Thanks, guys.